I'll be presenting attention mechanisms, a paper by Badano et al. So yeah, my name is Guillaume Chevalier. In French, Guillaume Chevalier. That's always a pain to pronounce in English. So here's the table of content. So I'll do an introduction of what was happening before that paper, and then I'll introduce attention mechanisms and the results, and then I'll open on some better neural architectures based on that. So, brief introduction. I'll cover the basics just to make sure that everyone has the required knowledge to continue to the attention mechanisms. So, you probably all know the recurrent neural network is just like a feed-forward network, but the hidden layer in the center has a connection with itself backward in time. So we can unravel that through many time steps at the right. So it looks like that. So we have 4 time steps where we accept inputs, and we can have outputs everywhere, and we will backpropagate through time. So we unravel the thing, and then we just learn on that. And the weights are shared from one instance to another. So there's the bidirectional recurrent neural network, which has 2 recurrent cells, which scans the information in different ways. So one is forward and the other is backward, and the output is just simply concatenated. So some people do an addition of 2 outputs, but we double the size because we concatenate it. And here are some stacked LSTM or RNN cells. So it's just stacking them one on top of the other, like just like deep neural networks. And then we have some depth problems. So it's simple, like you see at the top here. If there's not many time steps through the output, but if we add more, there's a vanishing gradient problem. So just to sum up, we have some informations, and it fades through time, and it's hard to learn from that at the output. So it's the vanishing gradient problem, and let's look at that. We have a tanh function, and if we took many nonlinearity, many tanh of that tanh recursively, or information shrinks. So if we derivate that, the derivative is small, so the learning is really small in the layers with depth. So that's not what we want. We want a solution. So there's the residual linear connections, or skip connections, highway, so the gradients flow more easily. Then we introduce the LSTM cell, the long short-term memory cells, which are an improvement on vanilla recurrent neural networks. So we introduce many other layers. If you have questions on that, I can answer them at the end. So yeah, we had some gating systems, and that looks like an output gate, forget gate, and an input gate. So we have an inner memory cell, which is linear through time backward. So that's where the residual concept is introduced in that architecture. So the forget gate and input gate both controls what we want to keep from the past as an information, and what we want to accept new from the input. So we concatenate the last output with the input, and we have that for calculating the gates, and we gate the input to the cell, and we gate the output to let some informations goes out. So in the paper of Badano, they use GRU cells, which are really similar. I think it's gated recurrent unit cells. So the only difference, or I should say the main difference, is that U there, how it works. So rather than having an forget gate and an input gate that are both different to let the information get inside the state, the inner state, we have something here, U, which takes the past input, the past hidden value, and we have 1 minus U, which lets enter the new information here, which is itself a small neural network of the past and the new information. So it's just like a switch, basically. It's, yeah.
So if you say switch, it means you can only take 1 or 0. You cannot take partial values.
So there's, well, I should say it's a slider. Yeah,
Okay,
you're right. So it's not binary, it's floats. And we take a sigmoid activation, or what's there? It's a
Oh yeah.
R and U.
So it's like a mixer.
See.
Sort of.
Yeah, so U is taken from a sigmoid. So if we take 1 minus the result of that, it's inversed. And we should remember that U is vectorial, so it's many neurons, and it's neuron-wise. So when we do the multiplication to gate it, it's neuron per neuron. So it's aligned. It's like it's not like a dot product. So yeah.
When were the GRU introduced compared to LSTM? Because LSTM are old.
Yeah. I don't know exactly when GRU cells were introduced, but I think LSTMs were there way before by Eugen Schmiduba. I'm not sure if I pronounced his name right, but yeah. So encoders, we have many time steps at the inputs. X is a vector in each situation, and we encode that through a state, a tout vector, we say. So we can take that tout vector and we decode it through time with a decoder. So this combined makes a sequence-to-sequence architecture. So we accept many things as an input. We build an inner representation, and we decode that. So we have only one vector in the center. That's a little bit of a bottleneck, and that's exactly what Badano et al. Will address in their paper. So
what do you mean a bottleneck? Is that a good or a bad thing?
It's a bad thing here, unlike the bottleneck layer, which is like a residual connection thing. This is not a bottleneck layer. It's a bottleneck, like I would say, because we have to read the whole sentence as an input and compress it in this small tout vector, and we have to unravel that with a decoder, and there's some loss of information. A tout vector, normally I think people code that like sequence to sequence. They code it with dimension size of 1,000 or 2,000 sometimes, so it's kind of huge also. But the thing is that it's really bottleneck. So if you have long sentences that you want to reply to, you're starting to lose important informations, because the encoder here, it's LSTM cells, but LSTM cells by their name are long short-term memory cells. So it's not made for really long time dependencies. So given that, yeah?
The encoding is done only for a sentence or the whole email?
Sorry, can you repeat that?
The encoding is done for a sentence or a whole email?
It can be what you want. So you can encode many sentences, but basically sequence-to-sequence architectures like that best works with only one sentence. But we will see that with Badano, what he introduces in his paper, we will be able to treat much more longer inputs. So yeah.
So maybe a follow up on Jeff playing devil's advocate, because a lot of architecture you precise.
I think that's usually a good thing.
It's a good thing that was
to
all
compress
like the autoencoder.
Yeah.
Of course, to keep what's good and throw away the noise. So
Yeah, but the intuition of Badano is, what if we could encode the tout vector for each word instead, and be able to look at that again later? Because when we read the text, let's say we're human and we read the text, and at the end we have like this tout vector, which is like a compressed representation. This is good, yeah, it can be useful to a lot of things, but if you want to scan the text and translate it, you will have to go back on every word, and just like if you want to do word by word translation, you are going to scan the text really slowly and go back on every word. So you want to be able to kind of go back in time and to distribute your attention where you want. So it's like our eyes, when we're reading text, we can move through it, and we're not limited only to the result of what we have thought about that text. So yeah, that can have a lot of useful applications. Sequence here with only a type vector, but let's see. Yeah, so translation. People encode. We train the neural network to learn to read text and output a translation. So there's like a feedback system here where we take the output and we just feed it back in the input. It's a little bit like if we're talking, we hear ourselves talking, and if we talk to a microphone, it gets a little bit weird in the beginning, because like if there's a feedback, you're not used to that offset in time with hearing back what you said. So here that's how we do translation, and by linking that back as an input, it makes the neural network more resilient into its learning. So it's correcting its self errors rather than just letting go what he already said, and you can be more conscious about what he just said to cope more during the training. So it's like having more variance in the input here compared to if we had just taken the generic previous word and let that go through. Yeah.
So just because I see two inputs, so I guess the squiggly one is the actual word, and the straight arrow is sort of kind of internal representation.
Yeah, it's the state. So the RNN is linked to itself one step back in time, and the input of the RNN is just exactly the output here. So it's like taking the output and feeding it back as an input. So that's an interesting concept.
So
And
quick question. At the test time, how do you know how many units do you need to put in the decoder? Is it like until you generate EOS?
yeah, it's until we generate EOS. But right now, I think most libraries implementation, they use what's called buckets. So they create a neural network like an RNN with a few buckets, let's say 10. So they can accept 10 words as an input and maybe 10 more words as an output.
Okay.
And they bucket that to, they clone the neural network to accept more buckets. So it's already all unraveled through time in memory.
Right.
The neural network is big in memory. And if they feed on some small sentences, for the encoder, they pad things to the right, and they put some
Like
zeros to
end
the
of sentence, like those sort of they just pad like some like default character that says do nothing.
I maybe should have said they just align that to the right, and to the left they do a mask, so they multiply with 0 or 1 to say if there's a word or not to do the learning properly, or something like this. In TensorFlow, the implementation is called something like a dynamic RNN, I think, and you can have a second array that specifies the length of everything you feed as an input and as an output to do the learning. So basically you need to define the neural network in its big, all unraveled size, and when you feed inputs, you also add a mask that says don't learn on those extra neurons at the left and at the right, so we just center things correctly.
And at test time?
I think that's the same. So if we output EOS properly,
and the other ones are sort of turned off.
Yeah, and maybe there's some algorithms to just recognize that the other ones have been turned off, or yeah, that's something to code more at test time. A little bit of tweak, I think. So it has been discovered that inverting input sentences increases accuracy or blow scores. So rather than translating I think to je pense, we will feed the neural network with think I, je pense. So we reverse the inputs. Yeah, so I think this was bringing an improvement in accuracy of some, like of 1%, or if else it was 1 unit of blow scores. I don't remember exactly if it was, but yeah.
I think this is highly dependent on languages. Because some languages like English, you start with,
Yeah, right.
with I. With Japanese, a lot of things are flipped backward compared to our language.
Yeah, we'll see that shortly.
Hindi.
Okay.
So,
Is Hindi also left to right? I mean, like
Yes.
subject, verb.
Yeah, you could change the order.
You would change the order in Hindi.
Yes, you could change.
I see.
Yeah, but in some way it makes sense because if you invert the sentence, you get context from the
Beginning, so
from
you
the
can start
intro.
again.
But that's kind of silly. Like,
But for translation, it's not that bad because you want to have as much context as possible.
Yeah, so it's like reading the sentence backward and constructing a thought vector, and then you're ready to
Yeah.
start again to just unpack it. So that's a bottleneck here.
But it sounds like, yeah, I think Philip's right. I mean, it sounds like it depends on the pair of languages you use, no?
Yeah. 'Cause if
Yeah.
you have
It sounds like
a
it.
VSO language like verb subject object
Right.
or subject verb object.
But I would be tempted to say that if you put things backward in the encoder, you will kind of go backward through time to get a state of mind that is more like at the start of your sentence or something like
I
that.
don't know, like if you speak like Yoda, right?
Yeah, okay, that's a good point.
Unifier.
Well, I don't know.
This is Yoda style.
So,
There you go. You get rid of paper. YODA. You only decode.
Oh, no.
What?
Oh, no, that doesn't
So let's introduce attention mechanism to deal with that. That's exactly the problem in the end. So let's just define attention shortly before
Sorry, could
proceeding.
you go back to the problem? I was still laughing.
The problem of
No, the previous.
okay, I'll show the picture right now. It's well,
Oh,
here.
it's
So
not-
we have some inversions in the translation we do, and here there's only one in the whole sentence from French to English. No, from English to French. But in other language there's much more inversions. So yeah, that's how attention mechanisms works. So we have some distributed attention that we can view many things from one step in the decoder to just be aware of where we are looking at in the input sentence. So just to introduce that correctly, attention. So here's a nice quote from William James, something like 200 years ago, I think, or approximately. It was a psychologist or something, and he defines attention, and he says it implies withdrawal from some things in order to deal effectively with others. So that's really what we will be doing with attention mechanisms. So here's the paper by Badano and Kyung Yong Cho and Joshua Bengio. So Badano, yeah, Dimitri Badano. So their intuition. Why encode a single thought vector between the encoder and the decoder if we can have everything? So here at the bottom is the encoder. They made it bidirectional, so it's scanning the inputs through both times, and it's concatenated here with the little dots around. And they take that and they do some computations with, like, they view it as a mini neural network here, a sub-model in the model, and which can sum that up to the decoder, which has given some clues to this mini neural network about what does he want its attention be pointing to. So let's see, here the state will accept not only maybe some inputs and the previous state in the recurrent decoder, but it will also accept some information about the attention. So here's the C, it's this value here. So the C is the sum of every attention vector dotted, not dot product, but sorry, like pointwise multiplication. It's gated, so the attention is gated with the previous outputs of the decoder at every of the encoder at every encoder time steps. So we do that dot product. Not that. Sorry, I'm kind of confused, but we do that multiplication here, neuron-wise, at the end of the encoder, and we have our attention, which will cuts off some places just to keep a few. of the hidden encoder representations. So how do they calculate the attention? Here it's a softmax of the mini neural networks altogether. So their probabilities sums to 1 because of the softmax. And remember, softmax is like a maxed out network, but not exactly. It's a softmax. So it's like trying to take one item, but also keeping a smooth distribution over things around it, and make things sum to 1. So we have here 2 coefficients that we sums, and we multiply it by the outputs here. So we just it's equivalent to taking only one of those vectors, but we can like slice off a part of one of those and just take another one and merge that together with an addition here in the sum. So yeah, to conclude, the attention here, the A is that, and it depends on the sub-attention, and this is the mini neural network. So it accepts the previous state here, it's linked there, and it also accepts the encoded hidden thought for every word. So the attention is calculated separately for every encoder outputs here, and it depends on the previous state. So it's given then to the next state. So it's really an attention. So how do they implement it in their paper? It's like that, but they wanted to say that we can be creative in the way that we add this mini model here, this mini neural network. It can be different. So they used a combination of the previous state and the hidden state. So they add that together, and they took a nonlinearity of it, and then some weight vector here. So they get values here, which they can multiply every hidden vector to just let information go through, and exactly they limit their attention to small parts. Yeah?
I've noticed that in a lot of these RNN LSTM, they still use the 10H, SIMH, sigmoid activation functions, as opposed to RELUs. Why? Do you have an explanation?
That's a really tough question, but maybe I can give a little bit of my intuition. So let's go back in time here. We have some sigmoid here for the gates. So sigmoid as an image, its output is limited to 0 and 1. So they also use at some point some tanh here in the LSTM cells. Not bad, I know, because it's got a GRU, but in general for the LSTM, here it's a tanh. So here the tanh keeps values from -1 to 1, and we just gate that with the sigmoid, which is from 0 to 1, to just let some information flow through the inner cell. And I think that the sigmoid and tanh activation functions are quite good, but that their main disadvantage is that vanishing gradient problem here. But because of our residual linear connections that we have here with the addition neuron per neuron of the what's coming from the forget part of the previous cell dotted with the forget gate to make our new representation cell, which also accepts some other inputs from the dotted input gate and tanh here, all calculated from the previous information we had, like copies of the concatenation of the previous hidden layer output and of our input. So yeah, basically because of this addition here, if our forget gates are initialized in a way that's as a high enough bias to just let everything flow through at every time steps at the beginning of the training, which is TensorFlow's default implementation, by the way, things just flow through, the gradients can flow, and we're fine. So it's getting back in time quite correctly, and we only learn thus to forget at some points rather than also having many inputs. So this causes a new problem, which is called the exploding gradients problem, which is that if we initialize the forget gate to let everything flow through from the past of this inner cell, and that we keep adding things to it from the inputs, eventually we'll get big things in there. So our gradient will explode. So that's why we do gradient clipping with RNNs. And yeah, by the way, in the paper of Badano, they still use gradient clipping for their GRU cells with attentions. Yeah, that's another problem, but at least it's not as important as having something vanishing. At least informations flow through. And I think they say that if the determinant of their matrix air or something is over 1, it will explode, and if it's under 1, it will vanish, or something like that. It's maybe not the determinant, but there's a mathematical way of validating that things are correct in our learning. So yeah, GRU cells just combine this and avoid that problem by having a little like switch here, more of like I should say a slider to let information flow through. I'm sorry, I've said this is a neuron per neuron multiplication, so we can learn many different things, many different sliders, but thinking twice, I'm not exactly sure if it's neuron-wise, because here they have the dot symbol, which could be like if it was just a unit multiplying. But I'm more tempted to think that it's a vector here, that where every neuron is neuron-wise multiplying the other things. So yeah, I hope that answers the question correctly. So yeah, they implement it like that. So they have just this, I think it's a bit awkward here, the addition before the nonlinearity, but at least it's working. It's a very simple model, and yeah. No, thinking twice, no, this is not awkward, but I would have maybe done a 2-layer mini neural network, but they really just did the basic to do a proof of concept, and some people even use bidirectional recurrent neural networks for their just their attention mechanisms, which takes as an input also the previous states at every point. So there's a lot of research going on with that too. So yeah, if we visualize that, so we have our input sentence, which is encoded like in Word 2vec. You probably know it's an one hot vector for all the dictionary here, every words that's possible. And they have that, and they have a continuous word representation, which is like they embed that correctly. This can be done with Word 2vec in some implementation, and they say that in their paper they use, I don't know, I noted it somewhere. Yeah, there it's 620. It's the size of their word representations in the inputs. And their hidden layer has a length of 1,000. And by hidden, I mean the recurrent cells width. So here they take the bidirectional recurrent thing, the encoder. So they do just the concatenation here to give that to the attention system. So we're here. We have encoded the words from the bidirectional inputs, and let's have an intention. And here they don't seem to take back the tout vector and feed it again to the decoder. I would be tempted to do that, or at least at the beginning of the training shut it off, and then slowly toward the end of the training shut that tout vector on again so that it gets through this. Maybe they deactivated it because it was all getting through tout vector to get there without passing through the attention system. I don't know. Maybe they still use it. I'm not sure. But yeah, the attention system here, if we visualize it, so we have an encoder representation of a word. We add that to a little neural network here, which is the attention neural network, which also takes the previous decoder state, the cell state here as an input. And then we have some things which we can multiply with our words. So for this word, this mini neural network here, the second word, it accepted the second word, not the first. And it still accepted also the same previous state. So we do that everywhere, and we dot product, we multiply, sorry, here, and we sum that, so it sums to 1, because we took a softmax before doing that for our attention weight here. So this reminds me a little bit of the cosine similarity. In fact, I think in more recent research, some people used only one value here from the attention weight to really multiply everything, and some other people took like the whole vector to neuron-wise multiply that with the words. So if it's neuron-wise, it makes me think about cosine similarity. So it's basically one word times another. So we just normalize that after. So it's a cosine similarity. It gives the angle in the hyper-dimensional space or something like that. So it's the similarity metric between like a query and between our word. So it can be almost viewed as if our state was doing a query, and then everything that matches that query is taken, and in the sum it's the best, it's the most big element, I mean, so it's summed correctly and the query is returned. So that can be viewed like a little bit of like a search. So that's why in their paper they call their architecture RNN search. I prefer attention mechanisms for naming that, because search is maybe not that precise, or what do they mean by search. But yeah, it's that how does it work. So it's like if we were doing a query and we was checking for the similarity metric between your query and two other words. So yeah, that's really clever, I think. So here's another visualization. We have our decoder, which accepts attention from the encoder, and it sums this, and there we will take this word more than others, but we will also have a little bit of attention still to other things. But by the way, this is a sum, so the words are summed together. So it's like neuron-wise, we still have a mix of every word, but yeah, that's an attention system here. So if we expand that visualization, here we have our state, the thing that's going really like transferring from one step of the RNN to the other one. We have this state, and we take it, and we will take a mini neural network here, or some people do dot things or do different maths here, but we take a softmax of two values here, and we multiply that here, and because we have a softmax, only one thing will get out here. So we continue decoding, and this whole thing of getting back to the encoder and going back to the decoder to get the next time step value as an input here. We do this for every decoding step, so you quickly see that it's an n square algorithm complexity. So you have n elements at the inputs, and for every n elements at the output, you have to iterate through all of two. So that's n squared. So if you have really long things, you'll probably still want to split things into sentences rather than only the big text, and have sub-attention systems at the sentence level on top of that, or some recursive or more advanced architectures. So their results. So they try to translate here from English to French, and we can say that we can see that there are some inversions of words here. Otherwise, it would have been a perfect identity matrix. And also the size of the sentences can differ a bit. So here we can have like we see that French takes a little bit longer to write than English because the matrix is more high than wide. Things like that. So sometimes it's good to have the attention fixed on still two words at once, because here when we say la for la zone économique européenne, we only had de here. So we want to be able to to say is it la, le, le, or something more than what's available in English. So our attention can also deal with things like that. So that's why it is really an interesting thing to have the attention, because we can go back on everything and just be really patient and translate correctly if we want. So yeah, the visualization here, some things are inverted. So that's the same thing as this matrix, same. So here's the inversion of the things here. And now other results, well, it's interesting to see here that the French sentence is much longer, and La Syrie is taken from just Syria. Is it that? Yeah. So yeah, we add sometimes some small words and things like that, and it's not confused. Yeah, and it goes on, and there's some strange things going on with the quotation marks, or the apostrophes. So yeah, still it works. So they compared their architecture with inputs and outputs of length 30 and of length 50. So ENCDEC is the sec2sec model, like the basic one. So it's an encoder, decoder, tau vector in the middle. And for the RNN search here, which is their architecture with attention mechanisms, and with an attention mechanism, well, it's the same length. So they did it with the length of 30 and of 50. And also they show the results for their network trained up to the end of the training. So trained really long. So that's the really best result they can get here with the 50 star. And they compare it to Moses, which is another literature, but which was not using deep learning approach. So Moses was more of a classical approach. And here they have the result with all the words in the dictionary and with no unknown words, because with words embeddings, like in word2vec or what I've showed earlier, we cannot, we sometimes don't have some words in our dictionary, so we put an unknown label. And what's done most of the time is that if we get the attention back on that unknown word to translate something at the output, and we don't have that word, with the attention, the alignment here that is learned, we still can map an unknown word to an unknown output. So here, yeah, with no unknown, they get quite good results. They're better than the classical approach.
So higher is better here. What's the score?
It's the blue score.
That's the blue score.
So I once knew correctly what was the blue scores, maybe 2 or 3 years ago, but I forgot.
Just higher is better.
So higher is better?
Yeah, higher is better.
Then Moses is better than everything?
Not here for their architecture, RNN search 50, which beats them with no unknown words.
No,
if
no
we
words. Okay.
But
when it's all, then so.
Yeah, when it's all, they still get the best results in terms of using deep learning, but Moses beats them. So I think anyway, Google Translate as of 2016 released a paper which is the very best state-of-the-art neural translation system, which I will show shortly after. So they got inspiration from that that research, and they pushed it really far bigger, using big deep architectures, because here this RNN, you know, it's not too huge. There's a 1,000 hidden neurons in the hidden layers, and I think it was using some kind of special GRUs that were kind of having some feedback things. I don't remember exactly, but they used some of their other research to do that. But well, there's a lot of improvements built on top of that paper. It seems like unimportant right now, but there's I think there's a lot of things on top of that has been done. So just to look here, a visualization with their RNN search architecture, if they add more words they get clearly the best neural results in terms of deep learning. So if it was with the encoder-decoder architecture here, this curve here and this one here, with more words, it was really getting bad. And if the RNN search 30 here, sorry, so basically that's their results here, and they show that they keep a good score with longer sentences. So they beat the fact that there were time problems in recurrent neural networks. You know, like the LSTM was a long short-term memory cell, but not too long in terms of time. So here they can have a good score through many more time steps here in their sentences. So here's an example.
Right, it's interesting that also very short sentences don't work very well.
Yeah.
Like it seems like you want to have 20 sentence length of 20 to have sort of the best performance, but shorter than this doesn't work as well.
I've not checked exactly in the paper if this is like just a training or if is many trainings with the different sentences length. Yeah, that's interesting. I've tried to code some RNNs recently, and I was trying to do predictions on time series. So I was accepting some inputs at many time steps, and I was outputting a prediction of what will happen, like imagine a stock market or something. I was trying to predict time. And I realized that if I was training just an encoder and doing one output, the result was really bad. And if I was taking an encoder and a decoder to do my predictions, even if I just want to predict the first one output rather than many more, like with a decoder, training with more length through the future with LSTM cells or RNN cells is really beneficial, I would say. And to compare that, I have took my encoder and it had one prediction, and that prediction I put it back as an input. So I moved my encoder. I took back this small window of things to do the next prediction, and I took that many times. And the result was really diverging in terms of time series prediction. And if I had an encoder-decoder architecture trained end-to-end with all the inputs and all the outputs correctly, this was disappearing. So maybe that's what's happening here with the reason why. I don't know, maybe that during training, if we have an encoder-decoder architecture and that we have many outputs in a future for the decoder, it's like doing the regression multiple times, because in the end we sum up through the future values in our decoder when doing the regression. So that's maybe something that could explain that. But here again, I'm not sure if this, I don't remember if this here sentence length is that they trained the neural network at different completely with different sentence lengths, or if they just trained the 50 and 30 on that, which would be plausible too, because they use the 50 and 30 here to show those results. And if the 30 was too small, I think they could just hack things and make the sentence longer with those values, and they just take recurrent weights and they add more buckets for their testing or something. Yeah. So here's an example. So we have a sentence here, and what's underlined is what contains a mistake here in the translation if we do it with an encoder-decoder. So there's two mistakes here because the sentence is long, but with their architecture they get it perfectly right for this example. So there was an example here, a mistake here, and a mistake here and here. So an admitting privilege is the right of a doctor to admit a patient to a hospital or a medical center to carry out a diagnosis or a procedure based on his status as a healthcare worker at a hospital. So that's his status of the doctor. And here, the encoder-decoder was translating that to un privilège d'admission est le droit d'un médecin de reconnaître un patient à l'hôpital ou un centre médical, and then it gets weird, d'un diagnostic ou de prendre un diagnostic en fonction de son état de santé. So there's two mistakes here. So here there's just awkward, like how it's brought. the sentence just can't continue like that. There's a mistake here. And also here, in function of his state of health, here the translation was about the patient, but no, that's about the state of the doctor as a worker at the hospital. So there were two mistakes just with the encoder, decoder, and tout vector in the middle. And here with RNN search, they get perfectly, and it's even I would say, yeah, it's nice. So, was it better than Google Translate? Well, they compared source sentence and their outputs and Google Translate outputs and many other outputs of all this, but I shortened the table just to make it possible to show it to you. And here Google Translate has done, I think, 2 mistakes, and their thing was really correct. Yeah, further research is based on that. And Google Translate now uses 2 attention systems, maybe in a small different way, but it's attention systems. It's the same concept. So toward better neural architectures. There's an interesting paper here, listen, attend, and spell, at the Carnegie Mellon University, and yeah, with Google Brain. Now they took some audio here, so this is some short time Fourier transforms. They just took, I guess, the coefficients, like the square root of the square amplitude of 2 Fourier coefficients, and they fed that to an input encoder system, and they wanted to just put audio back on text. So here, how much would a woodchuck chuck? That was what was in the audio. So here, how much would a woodchuck chuck? So we see that the attention system got correctly the repetition here, and other details like that. So it's an interesting thing to do. And more recently, WaveNet, Google's big neural network that can synthesize audio that cannot be, for which the generated audio cannot be differentiated between is it a human or is it a machine. They use an approach with what's called dilated convolution. It's just convolution, but they are split apart in time, like if the input was already downscaled with some max pooling, something like that. Not exactly, but well, the most recent approach takes the input audio as is, just the height of the wave in the signal, not some pre-processing like Fourier transform or MFCC male spectrum coefficients or something like that. But well, that's interesting to see that it's possible, and I think it's a simple approach to start, because WaveNet was really huge. I mean, for generating 1 minute of audio, no, 1 second of audio, they needed 1 minute of computing in their big cloud servers. So, well, that's not very practical, but I mean, GPUs will get better, and eventually this will be probably like, how to say that? It's real time. Yeah, it could be real time one day. So there's another interesting paper, and I think most of you will be interested by that one, because I think most of you are doing vision here with CNNs. So it's show, attend, and tell neural image caption generation with visual attention. So here again, Bengio is everywhere. So yeah, in this paper, they take an image, they have a CNN on top of that, and then the feature map here, they feed it through an LSTM, which time step per time step goes back to see the feature map and have an attention on it. So it kind of decode with an attention what something is doing in an image, and it can caption the image. So here, a bird flying over a body of water. So it really looks at things like through time. So it starts with a bird, and it's highlighting the bird, the attention is there, and then it moves to the body of water, which is more like a round bird, and yeah, it gives I think it's impressive. So here, a woman is throwing a frisbee in a park. So at some point, the attention was here on the frisbee, and a little bit on the woman and other things in the background. And here, a dog is standing on a hardwood floor. Well, that's a mistake here because it's okay, but there's also like a bed which is it missed or something. And here another interesting result where a stop sign is on a road with a mountain in the background. So yeah, that really got it right. And how does that work? Is that they take the convolutional feature map here. So here there's like a convolution and another one, and there they got a small feature map. So it's like a 4x4 feature map with some depth here that's represented by the small vectors. So the attention here, they operate on depth as if depth was one word. So it's like if every square in that feature map was an output of an encoder. That's how they see it. It's just that here it's spatially arranged in time. And to show the attention map, they can do some deconvolutions or some things like that, like transposed convolution here, or I don't know, something. But well, the attention system is coming from the previous decoder state, so it accepts also the annotation vector they call it, which is on the depth axis of the feature map. They take that, they do the attention system, and they take it also here, the dark arrow, and they proceed with the sum of every of the 4 squares here. So that's the attention system. They do a query on the depth axis here. So they query, okay, I want to see that. So maybe they say, I want to see an object or just something to start the sentence. And then they do the attention system, and it returns something, and they use it. And maybe with that, they also know a few more things of what's happening in the feature map. So their next query here from this state for the next time step of the decoder, it will readjust correctly. So there's another interesting research, which is Google's neural machine translation system, bridging the gap between human and machine translation. And they have shown that their results are really close to human translation level by a few percents or something, or by a few small points on some bleu score or rouge score. So here is how it works. So they take the input, here is the encoder at the left and the decoder at the right. So they stacked many cells. They added residual connections here, just like some residual, like ResNet, or deep things. So they stacked LSTM cells really deep like that. And at the input, they took bidirectional LSTM cell rather than just a feed-forward one, which would be just in one way, one direction. So here, their goal in doing that was that they could peek a little bit at the future and bring that back to the beginning, to just let proceed the other forward networks having this bit of state information here of the future of the sentence. And they did not do that on every GPU or on every layer, I should say, because they wanted to parallelize their processing. So there was a GPU 1 here, a GPU 2, and etc. And why did they do it that way, not using bidirectional everywhere, is that before even getting to the first step here, it needs to go forward and also to go backward. So we need to wait linear time with bidirectional cells before proceeding to the next output calculation. So the GPU above would be idle while it was doing that. So they just did it once in the beginning to just capture some context in the future of the sentence in the 2 ways with the bidirectional cells. And after they just stack many recurrent cells. So here, if they start with GPU 2 on their recurrent cell, if it's already at the second time step, the GPU 3 can already start with here as an input the already processed first node. So yeah, that's how they built something that was highly efficient. So they got the attention here with some softmax and things before getting into their decoder, which is some stacked residual cells again. So yeah, just to show you how those residual LSTM works, imagine like a residual convolutional connection. It's just taking the input of the LSTM, and when it processes it, let's add back the response to the input. No concatenation, nothing too strange, just an addition. That's really simple. That's like plus equals in TensorFlow. So let's just do that to the top. And yeah, that's how their bidirectional things works here. So meanwhile, maybe not meanwhile, I should say a little bit after, while I was in Sweden at the end of 2016, I was working on a small project of human activity recognition using stacked residual bidirectional LSTM cells. Well, that's a long name, but anyway, I couldn't find something best to describe that. So basically, I was working on a problem that was to identify what is someone doing from looking at his phone sensor data. So for the big recurrent neural network here, here is an input. So we had 128 time steps as inputs, and this is a simplification, a simplified view of our architecture. So we had like bidirectional cell here with a concatenation of the two directions, and then we had some ReLU hidden layer which was taking this concatenation to put it back to the size of which it was before, to not double the size at every time. So we have another bidirectional here. We have a residual connection, just like they're doing here. So we were calling that here a residual block, which we were stacking on top of another one. So one residual block, two residual block, and as you probably know, when you take a residual block, because of this addition here, things get big with big values when you do the addition. So that's why we also used a batch normalization layer here before the output, just like what's happening in the convolutional neural networks, say. So I was working on that, and then that's only after that I read their paper, and I was like, no way, they didn't do that like I thought, or something. Like, you know, during my project, I had read only the residual, like ResNet paper from Microsoft, and some other things like bidirectional, and yeah, you know. So I was trying to do that on my project to improve the accuracy, and then Google just I find that Google did that like 2 months ago or something, and translation. So that's
You get scooped.
huh?
You get scooped.
Well, I think they started working way earlier, and anyway, their model is for translation and mine is for activity recognition. So yeah, yeah, that was pretty fun. But here, just notice our model was bigger than that, because here we show two stacked blocks, each having two LSTM layers, which are bidirectional. But in reality, we had three LSTM layers. So we had two additions, another one for another layer. And we had three of those blocks stacked together. So it was an 18 layers of depth, and it's bidirectional, so there was twice the number of LSTM cells in that, and it improved my accuracy on this problem, which I was before that solving with only two stacked feed-forward LSTM cells to have like 91% of accuracy, and with that I got having like something 94% of accuracy. Or something like that. But I think it could be better optimized. I have not spent too much time on that. I just did some kind of grid search. I could have used HyperOpt, which is a library on GitHub, which seems promising for optimizing things. So there's also another paper, teaching machine to read and comprehend, I think this one is really interesting. I will accelerate a little bit because I'm hitting too much time right now. But let's say we have a document here. Mary went to England, and we ask a question: what visited England, or something visited England, and we want to find the answer to that. So we proceed with an attention mechanism here on the document, which can be much longer than only one small thing like that. And here we will have this as input to some kind of decoder that will have attention on two things. It's like an encoder, decoder, and we do some things to get the final answer. So that's really interesting because we can learn to ask things in a text. So to not overfit their small and limited data, they replaced their all the names or something like that in their text with some entities. So let's say entities 114, and they were shuffling that sometimes. And if they ask some entity identifies something and an X, and so this is their question, blah blah blah. So then their attention model scans the text and finds the good place in the text where they should give that as an answer. So they find the X here correctly in the text. So yeah, that's very interesting. So they ask a question and it can show in the text, oh, that's here, that's your answer. So I would really like to see a Control F, like finding page application with that. That would be so interesting. So another parenthesis.
So just
Yeah.
second time was already over an hour. How many more papers you wanted to show?
Oh, that's like the end in some slides. So yeah, neural Turing machines. Just saying, yeah, they use attention systems here for their memory, for read-write systems, and there's also adaptive computation time for recurrent networks. Choose one. Maybe don't use attentions, but it's just interesting research where one cell can repeat through some time steps, and then with a threshold decide to get to the next one or something like that. Yeah, that's interesting. So that's the end. Thank you very much to all of you.
More questions?
Sorry, Guillaume, the paper talks about alignment,
Yeah.
and you didn't say anything about that. For you, is it the same than attention?
Oh, the alignment is, sorry if I hadn't put the attention on that, but the alignment is what is learned here. Not what is learned, but is a side effect of processing the neural network. So there's the attention going on. They take the input and they generate the output. And meanwhile, they had attention vectors for each time steps. So they just take that in a matrix, and that's what they call the alignment. So they aligned words together to produce good outputs. So here's what it is. Yeah, thank you. So any other questions?
Well, thank you very much for your presentation. Very interesting.
Thank you.
The